All right, so now that we know how to name alkanes, we want to talk about a consequence of the fact that these carbons can be branched in any number of ways, and that is that many of them can have different structures with the same molecular formula. So this brings us to the idea of what we call constitutional isomers. So let's talk about these names. So isomer, iso means same, mer means formula. It's like the same molecular formula. Constitutional, that means the way that it's composed. So it's like, how are the atoms connected to one another? If it's a constitutional isomer, that means that the two molecules that you're talking about have the same molecular formula, but they have different chemical structures, so different connectivity. So like here, for example, we have hexane versus 2-methylpentane. If we look at these, they both are C6H14, so they have the same molecular formula, yet, as you can see, they have different structures. And because they have different structures, we know that they're going to have different properties. This is something that's very important to be able to recognize. One consequence of constitutional isomers is that the more carbons that you have, the number of constitutional isomers that are possible increases. So for example, with 1, 2, or 3 carbons, so methane, ethane, propane, you only have one possible isomer. There's no more than that you can have. Once you get to 4 carbons, you could have butane, sure, but then you could also have 2-methylpropane, for example. So that's 2 constitutional isomers. Moving up to pentane, now you have 3. Hexane has 5 total constitutional isomers. Up to heptane is up to 9. And then from there, it really spirals out of control. Octane has 18 different constitutional isomers. Nonane would be 35. Decane would be 75. And then as we move up from there, it just blows out of control. And again, it becomes kind of exponential at that point. So one thing that we really want to be able to understand is we need to be able to recognize whether a structure is an isomer or if it's the same compound. And we have a few different strategies for doing that. So for example, we've got here different ways of drawing C6H14. So this is hexane, 1, 2, 3, 4, 5, 6. And then we've got 2-methylpentane. Those are the two that we saw before. Then we have 3-methylpentane, 2,2-dimethylbutane, 2,3-dimethylbutane. And then here, well, this looks like it's a different structure based on what we saw. You'd think of it as like 2-ethylbutane. But actually, if we follow our naming convention, we would find out, oh, the longest chain is actually 1, 2, 3, 4, 5 carbons long. And so it's 5 carbons long. That's actually a pentane, and it's got a methyl group on carbon 3. So this is 3-methylpentane, same as this. So rather than having these being constitutional isomers, they are in fact the same molecule. So it's important that we're able to recognize this. Now, there's a few different ways that you can do it. If you can build the molecules using your model kits here, which I'm going to bring out my model kit for our next section here, but you can bring out your model kit. If you can build it and you can overlay the structures right on top of one another, you know they're the same molecule. But the easiest way to do it is you can just do it looking at it just like I did right now. If you can name the compounds and they end up having the same name, then if you've named them correctly, then they are the same molecule. The IUPAC system is such that you can't have 2 different compounds having the same name. If you could, it wouldn't be much of a naming system. So it's good that that's true. So this is exactly what I did here, right? So 1, 2, 3, 4, 5, 3-methylpentane. And then here, you might think, oh, 2-ethylbutane, that's not the longest chain. 1, 2, 3, 4, 5, that's a pentane. It's got a methyl group on the 3rd carbon, 3-methylpentane. So just follow the IUPAC rules and you can figure that out as well. Okay, so let's go ahead and try to figure out what is the relationship between the two molecules that we have here. And sorry, it's left and right. This isn't exactly clear, but it's like this molecule, second, this molecule, and finally, this molecule, this molecule. And so there's 3 possibilities. It could be the same molecule, they could be constitutional isomers, or they might be not related. In other words, maybe they don't have the same molecular formula. So keep that in mind. Why don't you guys go ahead, give it a shot, pause the video, figure out the relationship between the pairs of molecules, and then we'll work on it together when we unpause the recording. Okay, I hope you took a little bit of time there and figured out the relationship between these molecules. Let's look at it together. So now here we've got, the easiest way for us to do this together, I think, is just to name the molecules. So for this one, identify the longest chain, 1, 2, 3, 4, 5, pentane. and then there's a methyl on the third carbon, so 3-methylpentane. Here we've got the longest carbon chain, 1, 2, 3, 4, 5, okay, and then there's a methyl on the second, so it's 2-methylpentane. So they both have 6 carbons, and if we counted it up, we would actually find that they both have 14 hydrogens as well. So they have the same chemical formula, but they have different names. These are constitutional isomers. Okay. Now, down here on the left, obviously 1, 2, 3, 4, 5, no substituents, so that's pentane. And then on the right, it's 1, 2, 3, 4, 5, but it's in a ring. So this is cyclopentane. So you might think that these were isomers just based on the names, but count up the number of hydrogens. So for pentane, that's 3 hydrogens here, 2, 2, 2, and 3. That's a total of 12 hydrogens. Cyclopentane, though, 2, 2, 2, 2, 2, that's 10 hydrogens. So cyclopentane, C5H10, pentane, C5H12. Different formulas, these are not related whatsoever. So we're just gonna say not related. Lastly, looking here, 1, 2, 3, 4, 5, that's a pentane. 1, 2, 3, 4, 5, that's a pentane. They both have the same name. They're both the same molecule. These are the same molecule. So go ahead, make sure you ask any questions that you have down below about this type of problem here. This is something that you're going to want to be able to do relatively quickly as the semester goes on. So let's clear that. And I believe we have just one more thing to talk about here for this lecture video. So, and that's the relative stability. So the way that we measure the relative stability of isomers is we're going to actually just figure out their heat of combustion. So this may be something that you remember back from general chemistry. You can measure the heat of combustion by combining something with oxygen and finding out what is the delta H for that reaction for 1 mole of whatever you have burning. So here, this is 1, 2, 3, 4, 5, 6, 7, 8. This is octane here. So octane plus 12.5 moles of oxygen. The delta H for this reaction, producing 8 moles of CO2 and 9 moles of water, is negative 5,470 kilojoules per mole. If you compare that to the branched constitutional isomers, so for example, you could have 2,5-dimethylhexane, or you could have 2,2,3,3 tetramethylbutane. These are all constitutional isomers. You actually get a slightly less negative delta H for the combustion of those reactions. So the one that liberates the most energy, that's the one that's the most stable. So we would say that octane, straight chain octane, is the most stable, followed by the doubly branched, followed by the quadruply branched here. You probably get the idea here. The more branches that you have in a constitutional isomer, the less stable it is and the less energy you're going to get out of burning it, out of combustion. So that's the way that we're going to measure isomeric alkanes from here on. And we're going to refer back to this periodically throughout this chapter and then on into the next 2 semesters. So let's keep that in mind. And I believe that does it for this lecture video. So go ahead, ask any questions you have down in the comments below on Canvas, and I'll see you in a bit.